Alright, so now that we've talked a little bit about the theory behind simple harmonic motion, we're going to do an example problem. So what you see here on the screen is on the right here, we just got a bunch of equations that we're going to be potentially using. And on the right here, or on the left here, we have the actual problem. So the idea here is we have the motion of a spring, the 2 kilogram mass, is plotted below. And you're asked to find a number of different things. First of all, you're asked to find the amplitude of the motion. The second thing you're asked to find is the frequency of the motion. And the third thing that you're asked to find is the spring constant, K, of the spring. And you can do all of these things simply by looking at the graph. Now, to do this, we're going to do them in order. First off, we're going to find the amplitude of the motion. Now, the amplitude of the motion is actually the maximum displacement from equilibrium, that d equilibrium max there. So what you want to do here is you want to take a look at your graph and you want to find where it is displaced at most from the 0 position here, which is the displacement from, or which is the equilibrium position. So if you do this, typically speaking, it's not amazingly hard. You just want to find the highest point of your graph. In other words, you want to be where you are farthest from the equilibrium position. And that'll happen like right here-ish, or alternatively, it's probably a little easier to do it right here at the origin, which we got in green here. All right, so to find the displacement from equilibrium at the maximum point, just find the highest point and see how far you are from the 0. If you do this, most people don't have a huge problem with this after you know what to do. Your displacement from equilibrium at the maximum position is simply 10 meters. It's literally just how far you are. All right, and it is a maximum. It's going to be positive. And for the first part, that's literally all you need to do. Right? Shouldn't be amazingly difficult. Now, the second thing you want to find is the frequency of the motion. So the frequency of the motion, uh, like so, I use F for the symbol. Just be careful when you open up a lot of books. They like to use like a Greek letter nu for the frequency, but that's really, really annoying because it looks like V. So we're just going to use F. Now, finding F, you need to figure out how many times this thing repeats itself per second. Now, visually, it's really, really hard to find F. However, you'll notice that F here is related to the period t. And the period t is simply how many seconds it takes for this wave to repeat itself. Now, for this one, you can actually figure out how long it takes the wave to repeat itself just by comparing two positions that are the same. Now, you can use any positions that you want. You can use maximums, so you can take two maximums here. You can use minimums, two minimums here. Hopefully you can see that, they're little x's. Or you can even take two 0 points that are the same. So this one here and say this one here, right, roughly speaking. Your period t is simply how much time there is elapsed in between them. So you can take that length of time, you can take this length of time, you can take this length in time. Now, this is where I usually struggle because I am real bad at reading things. I did this in front of 250 people, including experts in the field, and I said going from here to roughly here was about 15 seconds, which is hilariously wrong. When we go from 0 to like, I don't know, 20-ish, it should be around 20, not 15. So just make sure that you measure it properly. Now, what you'll notice is for these three lines, we can go from 0 to 20-ish, which is about 20. We can go from 5 to about, that's about 25. 5 to 25 also gives you a t of 20. Or we can go from about 10 to 30, which also gives you a t of 20. When you're measuring things like the period, simply the time it takes for it to repeat. It does not matter where you measure it. Now, with the period being 20, we have not actually found the proper frequency of the motion. What we need here is we need F. Now, when we have T, however, we can find F pretty quickly. Because at the end of the day, we know that T here is 20 seconds. So if we want to find F, we simply need to take 1 and divide it by 20. If you do so, you'll get f is 0.05. And the units of this will be hertz, or seconds to the negative 1. The reason why it's hertz is because the 20 down here is simply 20 seconds. And hertz simply means seconds to the negative 1. So that's two of the things we need to find done fairly quickly. The last one we need is we need the spring constant k. Now, the only place k shows up here is in the angular frequency. So k here we're always going to find mathematically. Now, to do this, however, you'll notice that we need mass, which we actually have here, so it's not a big deal. We can put in the mass here. We'll leave it in SI units, so our mass here is just going to be 2. And also to find k, we need omega here, the angular frequency. What you'll notice here is our period is directly related to the angular frequency. Right, so here we know that the period is 20, and we can rearrange and solve this to find omega. I'm going to use a W here, which is not proper, but whatever. We can find omega. If you've done it correctly, it's 0.31. The units are hertz, because this is an angular frequency, just like it was when we dealt with rotational coordinates. And so we can take that and we can put it right here in place of omega over here. If you rearrange and solve this, you can actually find k. And if done properly, what you will receive is k is equal to 0.20 newtons per meter. The units will come out exactly the same way they came out when we dealt with Hooke's law. And once we've done that, we've found all three things that we're looking for. So the idea here is the minute you find the period, it's always the easiest thing to find graphically. It's always related to both the regular frequency and the angular frequency. And the angular frequency is related to the spring constant in the mass. Right? Now, we didn't talk here about the phase shift phi. Typically speaking, calculating phi directly is not particularly helpful most of the time. So you'll often see phi here get left out. And that's perfectly fine. It just tells you when you started counting, or how much in time your function has been shifted. All right, so with that, we finished with this example.